In the last lecture, we studied eddy current. Now today's topic is self-inductance. We have studied what is inductance, what is induction. Okay, it is generation of induced EMF and current due to changing magnetic flux linked with the coil. Now this is self-inductance. So it is something like the generation of the current in the self coil. Okay, to understand this, let us consider the diagram given at my right, that is this one. We have considered a solenoid and a cell. Okay, let us consider this cell as the variable cell. Okay, variable cell, which means it is increasing or decreasing. So for example, for some convenience, let us consider this is increasing. Okay, INCREA as I, increasing current. Okay, variable current. So now whenever I tap this, okay, whenever I tap it here, then what will happen? The current will start flowing in this direction, which is changing. Okay, so let us first plot the graph how does it increases. For an example, so in one, this is time t. Okay, this is 1 second, this is 2 seconds, this is 3 seconds, and this is 4 seconds. Okay, and let me write this as 1 ampere, this as 2 ampere, this as 3 ampere, this as 4 ampere, this as 5 ampere. Okay, though the current increases very slowly, like milliampere, microampere, 1 microampere, 2 microampere, 3 microampere, but for convenience I am considering this. Okay, so I tap it here, I switch on the key, I close the key, then in first second this current has passed. Okay, how much current? 1 ampere. In the second time it has passed this much. Okay, in third second, in first, second, third, it reaches to this 3 ampere. In fourth, it reaches to this 4 ampere. And whenever I join all this line, I will get this kind of graph. Okay, so this is the graph of the current. Okay, so it is increasing. Okay, so the current is increasing. Now whenever there is change in the current, then there will be change in the magnetic field, because this is a kind of solenoid, and this solenoid will produce a magnetic field like this. Okay, like this. For an example, I will consider this, I will consider this, I will consider this, and again I will consider this. Okay, but just I am giving the arbitrary arrow like this. Okay, so this is the changing magnetic flux. So here is a changing magnetic field or changing magnetic flux. Now the change is either increasing or either decreasing, but the current is increasing, therefore this phi here is increasing. Okay, why the phi is increasing? Because the current is increasing. Now whenever current increases, the magnetic field also increases. How? We have studied in the last chapter that the magnetic field is equal to mu naught n I inside the solenoid. Okay, now if I remove all this mu naught n I, then I should get the proportionality constant. It means if current increases, the magnetic field increases. Now if the magnetic field B increases, then the flux is also increasing. So this flux is due to this solenoid. Okay, the flux is due to the current in the solenoid. Okay, in the solenoid or inductor. Okay, this can be termed as inductor also. For this I will make another video why it is called inductor, solenoid or inductor. So for the phi is due to the I in the solenoid. So I is changing. If there is changing current, then there is changing magnetic field. If there is changing magnetic field, then there is changing flux. Here we have considered the increasing magnetic flux. Now if there is increasing magnetic flux, then there must be what? There must be the current. Okay. So now this flux, okay, this flux, very important, this flux is linked with the solenoid itself, right? For an example, if I consider a coil here, okay, like this, if I consider a coil something like this, and I connect with a galvanometer here, then this galvanometer should deflect because of the change in magnetic flux linked with this coil. But I don't have coil here. Okay, this magnetic flux is linked with this coil itself. Okay, the phi is linked with the solenoid itself. It means that this changing magnetic flux will again produce the current in the coil itself. Okay, understood? There is no another coil. There is only this coil which is linked with itself. This flux is linked with the coil of the solenoid itself. Okay, so therefore there is induced EMF in the solenoid coil itself. Why there is induced EMF in the solenoid itself? Because this flux is linked with the coil of the solenoid itself. Now I am again saying itself. Okay, entire this phenomenon is called self-inductance. So definition is that it is the phenomena in which the induced EMF is induced in the self coil. Okay, in the self coil in which there is changing magnetic flux. Therefore, this is called self-inductance. Okay. Now, this self-inductance, produces the EMF, and this EMF is also called as back EMF. Okay, back EMF. Why? Because this is from the Lenz's law. What does this Lenz's law says? That Lenz's law says it should oppose the cause. Now if the current is coming from this side, it is coming towards us, so this is this and this is this, okay, from here going, and it is coming towards us and it is going down. Well, this is external current, okay, external current I. Now, because of the electromagnetic induction, self-inductance, there is EMF and hence there is a current. And the direction of that current should be opposite to the external current. Means that if it is coming, then the induced current direction should be in that direction. Okay? So, one should write that. Therefore, this is also called the back EMF. Okay? So, the direction of induced current in self-inductance is opposite to the direction of the external current applied to this solenoid using this variable battery or cell. So this is all about the self-inductance. Okay, so let us go to the theory part or some derivation of it. Okay, I hope you have understood this. So in theory, what we know is, we know that this phi, okay, is directly proportional to current I. Why? If the phi is more, there is more current. Say, if B is more, current is more. If current is more, then phi is more. More the phi, more is the current. So this is phi is proportional to I. Okay, if current is, if the flux, if there is more and more flux, then this current is more. And please remember, this current is induced current. Okay, whatever. Okay, I will not write this because you may get confused. So then I have to remove this, or I will write it is equal to L I. Okay, this proportionality constant I have to remove, and I will write where this L is a constant called coefficient of self inductance. Okay, coefficient of self induction. What is L? L is coefficient of self inductance. Okay, so let me write this as equation number 1, and also we know the EMF E is equal to minus N d phi by dt. Okay, and this negative sign is from Lenz law, and what is this? N is the number of turns in the coil. So let us write, let N is equal to 1. Okay, this is N, not M. This is N, and for number is equal to 1, and neglect the negative sign. Okay, then what do we get? We get this epsilon is equal to d phi by dt. Okay, so now let us go to the equation number 1, and let us put the value of phi in this equation. If I put it, or I should get EMF is equal to d dt is there, and what is phi? Phi is L and I. Okay, so this is how it look like. Now what I do is, L is a constant term, this L is a constant term, so I will take it outside, or I will get epsilon, that is EMF, equal to L di by dt. So this is the equation of EMF, or for self inductance. Okay, so somebody asks what derive the equation for the EMF of self inductance, then we should do this. Okay, so let me go to the topic of equation. So now next is equation of, this is simply the theory, equation of self inductance, that is L. Okay, so how do I get self inductance? So I can write L di by dt is equal to E epsilon. Okay, so let me write this is equal to epsilon over here. Then I need L, or this L is equal to epsilon divided by di by dt. So this is the equation of, what is the equation of? This is the equation of self inductance. Okay, so what should be the unit? Okay, unit I will write it here. So unit, okay, it has got 2 unit. I have here epsilon by di by dt. Okay, the SI unit should be, epsilon is EMF, so EMF has V, potential, divided by current has ampere, and time has second. So what is its unit? Its unit is volt per ampere per second is its unit. But this is a bit difficult and long SI unit, so it has got one special unit which is called, so SI unit is Henry, bracket में लिखो H. So SI unit is Henry. Now let us define 1 Henry. Okay, this is a complete lesson on this self inductance. So let me write the as 1 Henry, definition of 1 Henry. And we know that L is equal to epsilon divided by di by dt. To make this 1, what should be there? There should be EMF. Okay, this EMF is equal to 1 volt, and di by dt should be also 1 ampere divided by 1 second, which is equal to 1 ampere per second. Then what will happen? EMF is also 1, di by dt is also 1. Then I should get L is equal to how much? This is 1 V divided by 1 ampere per second. Ampere per second. So from this I will define this is equal to 1 Henry. Okay, if everything is 1, this is also 1, so it will become 100. Now what is the definition of 100? When the EMF of 1 volt is induced in the coil by change in current of 1 ampere per 1 second. Okay, when there is induced EMF equal to 1 volt due to change in current by 1 ampere per 1 second. Okay, so this is very simple. There is one EMF of volt by changing current of 1 ampere by 1 second. At that time, that EMF is called, this condition, we get 100. Inductance at that time is called 100. When there is a generation of 1 volt of EMF by changing current by 1 ampere per 1 second. So in 1 second it is changing 1 ampere here. In another 1 second it is again changing 1 ampere. 1 to 2 is 1 ampere. From 2 to 3 seconds it is changed by 1 ampere. So the 1 Henry is the EMF. 1 Henry is when 1 volt of EMF is produced by changing electric current by 1 ampere per 1 second. That time the inductance is called 100. Okay, so the next topic is mutual inductance. Thank you.